Hi, I'm Matt, and thanks for coming to our talk. Our research examines the uses of discrete Fourier transforms, or DFTs, in music studies, and in doing so connects concepts of chord spacing, chord quality, and timbre. We'll start with an introduction to the DFT. Here's a spectrogram of the following chord. So this spectrogram is a Fourier transform of the audio signal we just heard. But how do we get all of this information, and how does the Fourier transform work? The DFT is an equation which breaks down a signal into its constituent sinusoidal parts. So, given an input, the DFT will return Fourier components, Fn, where each component corresponds with some type of sinusoid. Each sinusoid has magnitude and phase, although we'll only look to magnitude in this paper. Perhaps one of the most common uses of the DFT is in the audio domain. Given an audio waveform, the DFT will return components n, where each Fn is a division of the signal into n equal parts. So for example, F6 is a division of the signal into 6 equal parts. So if we zoom into the audio file that we just listened to, see here that this specific sinusoid matches really well to the signal. This sinusoid corresponds to the fundamental of G3. So we might say that since G3 corresponds well to the signal, that the signal has some element of G3. So going back to the spectrogram, the bold yellow in the bottom of the graph shows that there's a high magnitude for G3.
Hi, I'm Noah. So with that introduction of the DFT in mind, we can now highlight the central contribution of our paper, which is to focus on a hitherto unnoticed similarity between Kepstrom in timbre studies and chord quality in music theory. We use a hybrid approach between these to study chord spacing. So just to summarize previous approaches, let's start with chord quality. So with chord quality, we begin with the 12 pitch classes, or chroma, and encode these in a vector of length 12 that says which of these are or aren't in the chord. Put this through the DFT, and that gives us 6 distinct components, which tell us about the intervals in the sonority. This is useful in some corpus studies, such as those by Jason Yust. The DFT is also used extensively in timbre research, of course, most notably to go from a waveform to a spectrum, and I imagine that as this is a timbre session, that use really needs no further introduction. From the spectrum, however, we can take another DFT and get what's called the Kepstrom. The regularities in the spectrum in terms of frequency space, shown by the blue waveform up top, correspond to a missing fundamental, which is shown below in the Kepstrom. Circled in blue is its quiffrency, which is equivalent to its period. The pink envelope, meanwhile, is the general shape of the whole spectrum, accounting for a lot of its piano timbre, and that'll correspond to the first few coefficients of the Kepstrom. These coefficients, especially when converted to so-called mel-frequency Kepstrom coefficients, are very useful for computational timbre identification, although they are considered to be cognitively opaque, though they do have a few interesting behavioral correlates. So what's our contribution? Well, we're arguing that you can productively study chord spacing by combining aspects of both of the approaches. So like music theorist, chord quality will work directly on pitch data rather than frequencies. Like the Kepstrom, we won't use octave equivalence, we'll just work directly over the whole range of possible pitches. And this fits nicely with a lot of other work on synthesizing pitch and timbre research that's discussed a bit more in our paper. So the rest of our talk will have 3 short parts. So firstly, we'll talk a bit more about what the PDFT is, how it's calculated, and how to make sense of the results. And then we'll go through 2 short computational experiments. So in the first one, we'll look at how our PDFT differs from the pitch class or chroma DFT, or chord quality, on assessing which chords are similar or different. And in the second one, my co-author Matt will talk about how some specific PDFT components correlate with previous perceptual judgments made by musically trained listeners. So first, how is the PDFT calculated? Well, we can code pitches in terms of just their MIDI values, and then make a vector of whether or not each note is in the chord, and that'll be of length 128. To avoid wraparound effects, we'll zero pad it by just adding another 128 zeros to the end, run it through the DFT, and then we end up with 128 components from our 256th length vector. And then of our resultant components, the first component would correspond to just a single big division of the whole space. And the 11th would be an 11-part division, and so forth. So as an example of how to interpret these, here's the opening chord from Debussy's Sunken Cathedral Prelude, which sounds like this. So you can see all the way at the left, we have a prominent peak corresponding to a spacing of 4 octaves, which is, of course, one of the most distinct features of this chord. Then we have later peaks for the octaves within each hand, as well as the smaller intervals within each hand. So for experiment 1, we calculated 50,000 random chords and asked how they compared to Debussy's original chord, specifically measuring their similarity under both PDFT and PCDFT to the original. More technical details on how the chords were generated and how we measured that are in our paper. So even though the two measures do have a general correlation, as we can see here, we picked 2 outliers to show how they differ. So first we'll show you this chord that was identical by PCDFT, but pretty far by PDFT. Let's compare them orally. So we can see they're literally the same 2 pitch classes, or chroma, D and G, but they're spaced very differently. Open fifths and octaves versus a single 11th. So correspondingly, looking at the PDFTs, we see there are basically no peaks at the same places. There is something in the 40s that's pretty similar, but by and large, peaks of one are not peaks of the other. It's no surprise these are far apart. For comparison, here's a chord that's very far by PCDFT, but relatively close by PDFT. Let's listen to them side by side. So we can see they're completely different sorts of pitch class sets, an open fifth versus a mostly whole tone-like collection. But when we look at the PDFT, they have a lot of peaks in common. They both have 4-octave, octave, and fifth spacing, and a lot of the circled peaks are in common, and these 2 PDFTs have similar overall trajectories and envelopes. And correspondingly, they do sound somewhat similar in that they both have that characteristic same sort of wide spacing.
So for the second experiment, we wanted to investigate whether or not our model would correlate well with subject responses. So we decided to compare our model to Cusi 2005. In their original study, Cusi studied subject responses for 4 different set classes with 4 different chord spacings. Subjects were asked to rate chord proximity using words like closeness, resemblance, and similarity on a 7-step Likert scale. Each chord was paired with every other except for those that shared the same chord span, so the largest spans were not paired with the other largest spanned chords. The study used both musically trained and less trained subject, but since the trained subjects were more consistent, we'll restrict our discussion to the trained subject responses only. In the initial experiment, Cusi showed that subject responses were more in line with chord spacing than set class similarity measures. So we hypothesized that our model, a model that takes in chord spacing, might be a better predictor than some of the pitch class similarity measures. Unfortunately, our model corresponded to subject responses with a Pearson's R of 0.38. This is still below some of the better performing pitch class similarity measures, which had a correlation of 0.43. So in a post hoc fashion, we decided to unpack the results a bit and figure out why, if our model accounts for chord spacing, it was still a poor predictor of subject responses. By using a stepwise regression method of choosing components which added to the correlation values of the subject responses, we were able to figure out which components were most relevant to subject responses. There were 49 in particular, resulting in a correlation value of 0.74. A quick disclaimer that because this was all done post hoc with stepwise regression, our data might overfit the subject responses. For now, we can form hypotheses from these post hoc results, but more experimenting would be required to evaluate such hypotheses. So to further evaluate the results, what we did is we took individual PDFT components and correlated them with the subject responses. The yellow dots in the visual are the 49 components which factored into the stepwise regression. What's interesting about these 49 components is that they tend to group together in areas. Further evaluation would show that these areas correspond with certain divisions of the space. So for example, all the way to the left where there are a lot of yellow dots corresponds to wide spacing of the chords. Towards the middle we have the thirds, and then towards the end we have fourths and seconds. This suggests that subjects are prioritizing certain intervallic qualities of the chords over others. In line with Kuzi's conclusions, there are a lot of yellow dots by the lower components, corresponding to wide spacing. This type of chord quality can't be accounted for by pitch class measures. We hope both of our experiments have shown that the PDFT captures salient perceptual aspects of chord quality and spacing. In connecting interdisciplinary research through the DFT, we positioned our work within the growing literature connecting pitch, harmony, and timbre. We look forward to following up on our post hoc analyses, and we welcome any comments or questions. Thank you.